Thiago Tomei. I am a researcher at the Nucleus for Scientific Computing of UNESP. I'm a member of the São Paulo Research and Analysis Center group, SPRACE. I work in the LHC. I work in the CMS collaboration. I couldn't attend the introduction this morning, I'm sorry. Just 1/2 minute about myself. I was also a student here at IFT-UNESP not so long ago. And then I had a postdoc at CERN, and then went back here at IFT, and then I was hired at the NCC, Nucleus for Scientific Computing in Portuguese. My main research area is, of course, LHC physics, particularly physics beyond the standard model. I use it to search for new resonance, new particles beyond the standard model. And now I still do that, but now I search for dark matter. I am unhappy to report that up to now I have found no new physics, but here's hoping that that will change. And I have been volunteered to give you this course about aspects of experimental high energy physics, which you may find a little bit awkward because I'm pretty sure that when you signed up for this, it was the journey into theoretical physics. So you may think this is a surprise, but I'll promise to make this nice for all of you. So there are 4 lectures, okay? This actually is a theoretical lecture. It's an introduction to the standard model. Next time we'll speak about accelerators and detectors. We'll go onwards onto data reconstruction, and we'll finish with data analysis. Data analysis, in a very particular sense, is what we experimental physicists, some of us would call, this is the real physics that we do. And all of the rest is preparation. This is not true, okay? Data analysis is really the most interesting, the most funny, the thing we have joy in doing. But the thing is that without everything else, there is no fun to be had at the end. So reconstructing the data, projecting, designing and building your detectors and calibrating the detectors and running the experiment is also important. You cannot eat the dessert at the end if you don't eat your vegetables, right? So, and of course, it's useless to try to do experiment if you don't have at least a bit of theoretical understanding. A lot of theoretical understanding, I would say. So this is what this first lecture is about. Now, of course, I have no illusion whatsoever that I'll be able to teach you the standard model of particle physics in a 1-hour lecture, okay? Now, everybody, not only physicists working high energy physics, every physicist should have at least some knowledge. But if you want to do high energy physics, you should have a strong knowledge of the standard model. 1 week, 1 lecture is not enough. 1 week is not enough, and I'm tempted to say that 1 lifetime is not enough. The more I study, the more I come to the conclusion that I know nothing. And this is true in a very, very specific sense that I don't know if you people have had the cosmology talk already or not, but if you look up in the sky and try to see what the universe is made of, not only our planet or the matter around us, but everything, you'll find out that that a new kind of matter exists or seems to exist. You can see it from gravitational experiments. That seems to have nothing to do with what the standard model tells us. And then there seems to be something else, which, for the lack of a better name, this new kind of matter we call dark matter, but this is just a name because I have no idea what it is. And then there is something which is called dark energy, which we have even less idea. When I tell this to my friends, they think I'm making fun of them, and for good reason. So what I'll try to give in this lecture is not a complete panorama. It's something of a treasure map. And as every treasure map, I'll try to show you the way to understand the standard model, and I'll highlight some features that I particularly think are interesting. But of course, as every treasure map, it is definitely not complete, and sometimes you will not understand it. And of course, you will not understand it because I failed to make you understand, of course. You are brilliant, definitely. I'm not joking. I would like to thank Professor Novaes and Gregores and Professor Ponton, who live in our hearts, for their contributions to this lecture, okay? Because again, I am an experimentalist, and I'll be honest, I'm not sure that I'm the most qualified person in this room to give you this talk, but I give you my best. So after we finish this map, if you want to keep searching for the treasure, there are more references that you can follow. There is this review paper, and then there are books by Haus and Martin and Langacker that go into much more detail into the structure of the standard model. So if you're ready, I think we can begin. And of course, if anything is not clear, please feel free to interrupt me at any time, okay? So the standard model, what is it about? The standard model is a quantum field theory based on gauge symmetries that tries to describe electromagnetic interactions, weak interactions, and strong interactions. What are those things? We're going to see soon. But the first thing that I want to draw your attention to is the fact that the standard model reproduces extremely well the phenomenology of all observed particles. Experimental physicists, high-energy physicists, have come to the conclusion that this is even boring, okay? I was not joking when I said, unfortunately, I'm happy to report that we have found no new physics. For the last decades or so, the story of experimental energy physics has been a story of confirmation and confirmation and confirmation and confirmation of the predictions of the standard model, which is nice because it shows that the standard model is a good theory, but it's a bit boring, you know. There is no the eureka. There is no, that's funny. And of course, it's a theory, but it's extremely based on the interplay in between experimental discoveries that happened during the last century and theoretical developments that took the state of physics at the end of the 19th century, which was I think it was Lord Kelvin who had decried, oh, physics is over. Classical physics is over, and there is nothing else to be done. And then on one side, we got relativity. On the other, we got quantum mechanics, and then the whole story changed. So one of the biggest developments in physics in the 20th century was the rise of quantum field theory, which, again, I'm going to speak about, but I have no illusions of teaching you quantum field theory, but has this fundamental idea that particles, as we know them, are quanta, are small packets of fields. This idea may already pick your brain a little bit in the sense that you know that photons exist, but you have learned that the electromagnetic field is, well, a field. So you already have these ideas in the back of your mind. Quantum field theory is the way we work with this and formalize it. And it comes from the marriage of quantum mechanics and special relativity in a very particular sense. And then the other powerful idea was the idea that invariance fields and combinations of fields can be invariant under transformations. You transform the fields and those functions according to certain rules. And what are these certain rules? Transformations that belong to symmetry groups. And then the form of the interactions, how the fields interact among each other, it comes as a result of these symmetries. And this is a bit more strange idea, but I'll try to give you the map. The standard model made a lot of successful predictions. It predicted the existence of neutral currents. It predicted the mass of the W and Z bosons. It predicts that there should be equal numbers of leptons and quarks in the isospin doublets, and that there should exist at least one scalar neutral boson that is the Higgs boson. Half of these words probably make no sense to you now, but you will see later. I am legally obligated to show you this poster, okay? The community of high energy physics tries to put all of this information in one poster that's usually distributed to schools, universities. And you can download copies of it in this website here. Here, of course, you cannot read it, but when you download, there will be a clickable link. I want to flash two plots first. How good is the standard model? And here is the answer. One of the answers. What is this plot? This is what we in CMF, my experiment, we call the Starway to Heaven plot. This is, in gray here, you have the theory predictions for a series of processes. And the different colors, red, blue, and green, they are for different operation modes of the Large Hadron Collider, 7, 8, and 13 TeV. And you can see, where you can see, of course, that the standard model prediction and the measurement, they are always on top of each other. What is the exception? The exception are, for instance, places where we didn't still manage to measure because it's hard work. So for instance, here, the standard model prediction is this gray square here. We couldn't measure it because it's too small. But then we put a limit, and the limit is this bar here that's actually only upwards. And it says, I didn't manage to measure, but I'm sure that it's 95% confidence level, sure that it has to be smaller than this. And you can see all of these agreements, all of these, did anybody say something? Sorry. You can see all of those agreements in different channels, in different processes. Another plot, which is a little bit more famous, is this one, which comes from the Lab Electroweak Working Group, which shows all of these are predictions of the standard model, and the measurements of the actual measured values when you do a global fit of all the parameters to all the observed data. And here the axis is the pool. The pool is how many standard deviations, how many sigmas, as we say on the jargon, they are from the predicted value. And you can see that you have what you expect if you're right? Almost every observable is within 1 sigma. You have some in between 1 and 2 sigma. And of course, you have one that has to be close to 3 sigma. And then people look at this and try to write papers explaining why this could be hints of new physics, but matter of the fact, the statistics, if you measure enough things, some of them will be 3 sigma away from your prediction. So, as I told you, quantum, the standard model is a quantum field theory of gauge fields. There are 2 parts to this sentence that I will try to unpack for you. First, quantum field theory. This, as it stands right now, is our best tool for describing the fundamental laws of nature. And why is that? Because quantum field theory is a coherent way to combine the principles of quantum mechanics with the principles of classical field theory, which is relativistic by construction. If you try to do relativistic quantum mechanics and try to take the wave function, let's say, and try to make it become relativistic by, say, imposing the, instead of the wave function describing the energy momentum relation of classical mechanics, you try to make it follow the energy momentum relation of special relativity, you will get equations. Sure, you'll get the Klein-Gordon equation or the Dirac equation. But it will not work. It will lead to inconsistencies. Because that's the wrong way to describe it. What you actually want to do is that you want, instead of thinking of wave functions of one particle, you want to think of fields that are sorta, kinda like the wave functions, but it's not quite the same thing. And then you want to say that these fields, they have dynamical degrees of freedom, as every field does, right? And to quantize, you want to make these degrees of freedom become operators. What do you mean operators? These I didn't write, but I'll just tell you. Remember back when you solved the harmonic oscillator many years ago in quantum mechanics that at some point you managed to write like a dagger? What you did there was that you wrote the Hamiltonian of the harmonic oscillator in terms of those operators a dagger. But the Hamiltonian is what describes the system. What you can do now, and what is done in quantum field theory, is that you take the Lagrangian or the Hamiltonian. Usually we do it with the Lagrangian because we're doing field theory, and try to describe it using these operators. But then the field is defined everywhere in space-time. So you have to have operators in every point of space-time. Speaking like that is super easy. But of course, the mathematics and the amount of calculation that you have to do is extremely hard. What's the upshot? The upshot is that when you do that, you have quantum fields that obey commutation relations at every point in space and time. And if you run the calculations, it will come out that the interactions of the fields are local. The fields interact amongst each other only at a local level, only when they are at the same x, y, z at the same time. Then there is no action at a distance. The principle of relativity is safe. This is one half of the story, but when you combine this with symmetry postulates like Lorentz symmetry or gauge symmetry, then we will see that it will also help to describe interactions. Now, we don't need to go to interactions just yet. Just with free fields, fields that don't interact with anything, this will already give you indistinguishable particles. Why are particles indistinguishable? Why are all electrons the same? Because they are all excitations of one single field, the electron field. Antiparticles. Why does the positron exist? Why can't we just make do with the electron? It comes out naturally from quantum field theory. Why do the electrons, this one's hard. Why does the electron have spin half and is a fermion? Why is there a connection between spin and statistics? This is something that also comes from quantum field theory, but this comes already at a more advanced level, okay? But also this came, if you remember your undergrad studies, you'll remember that this came from above. But now, in quantum field theory, this can be derived. If you add the interactions, you will find then processes which create and destroy particles and interactions which exchange particles. And you will see something. Here, I'm following Professor Ponton very closely because he knew much more quantum field theory than I do. What's a particle? Let's follow this. Consider this state which has a particle of mass m and spin s, or illicit Th, in the case that's a particle that doesn't have mass. And then you have this state like this, and then you have operators that get the value of the momentum, the value of the energy, and it has to be relativistic energy, and the value of the spin. Now, remember, we want to do relativistic quantum mechanics, so quantum field theory. This means that the Hilbert space that's spanned by these vectors has to contain all the state vectors for all momenta that have we call this on the mass shell, but which follow this relation here. Why is that? Because you can always have a particle that is stopped, and then you can do the Lorentz boost on it. You have to have in your Hilbert space the state vectors for all of those particles, no matter what the boost. And then you can also label by the spin. This is just what you know from quantum mechanics, spin 0, half, 1. And on top of that, you have internal charges. Electrical charge is the one you know, right? You know that particles have charge. We will see that there are other numbers. what's the deal? Remember in the quantum harmonic oscillator where you had the vacuum state and then you went up and down by using a dagger? We borrow all that formalism wholesale and apply it here. And we say, how do I create a single particle in the universe with these quantum numbers here? You take the vacuum, the state with no particles, and use the dagger. And then you create one particle with these quantum numbers. And if I want to create two, I will go with another A dagger. It's strange, isn't it? But it becomes easier later. Assuming that you're on board with this formalism, the difference in between bosons and fermions is just that if you want to make a theory of bosons, you have to impose conditions on the commutators of the dagger, while for fermions you impose conditions on the anti-commutators, and then you have these relations while all the other vanishes. And then if you want to have non-interacting particles, it's easy. You just apply as many A daggers as you want. And if you apply an A dagger and then an A with the same quantum numbers, the particle is destroyed. And if you apply an A dagger with, if you apply an A with, in a state where there is no particle, you will destroy the vacuum. Exactly what you know from the quantum oscillator. Now, notice how this immediately gives you indistinguishable particles. The only thing that these states have are their occupation numbers, right? Oh, you have one particle with this, and this quantum number. You cannot say which particle it is. You just know there is a particle created by the A dagger. But those are the only things that it has. It doesn't have any other information. So if you have to, you cannot distinguish from any other particle that was created from this from the same operator. What do we do with this? First, we put them all the particle momentums, one particle momentum states together. So we sum and integrate over all the momenta. And this is, of course, Fourier transforming. And then this gives you immediately the field defined at a place in space-time. Now, you can do the same with other operators. And this is related to the fact that if the particle carries a charge, then you have a distinct antiparticle, and this will give you another field for the antiparticle. And then if you define this field here and use the commutation relations in this slide, you will see that the commutation relation now defined for this field, which is this big sum over operators here, this commutator is going to be 0 for any space-like separation in between the two space-time points. What does this mean? This means that the field is causal. This means exactly what we want from the principle of relativity. Fields that are space-time separated do not have causal relation. So just by imposing these conditions, we already got everything. We already got locality, we got causality, we got indistinguishable particles. So it's powerful. Of course, I don't expect I expect 0 of you to actually have understood all of this. But this is the map. Now you open your favorite quantum field theory book and study this and do the exercise. But this is the gist of it. Now, the interesting thing is that, again, if you take this field, it will satisfy the Klein-Gordon equation, which is this one. What is the Klein-Gordon equation that I have been speaking about? This is del mi, right? So you can notice that this thing here, it embodies the relativistic energy momentum equation, much like the Schrödinger equation embodies the classical energy momentum equation. So every field, every relativistic field has to obey at least the Klein-Gordon equation. You can have more conditions on it if it is a different kind of field. For instance, Dirac field has to obey some extra conditions, but every relativistic field has to obey this because this is just the energy moment relation. And then if you want to do it in real quantum field theory, what you do is that you take Lagrangian density, run the Euler-Lagrange equations, and you get this equation back. And then I'm just flashing it here for you. But then, of course, you can have different Lagrangians, run the Euler-Lagrange, and get equations for other kinds of fields. For instance, you have for spin-half particles, or for the electromagnetic field. This one you should know. This one is purely electromagnetism. And if you do the same thing, you get the Maxwell's equations. So this is one half of the story. Let's make quantum field theory to try to describe the world. And let's think that the particles are excitations of this field. And doing that, you get all of the good stuff, indistinguishable, spin statistics, and causality. But free fields take us nowhere, right? An electromagnetic field that doesn't interact with anything, okay, it's nice, it's a wave propagating in the universe, but nothing actually ever happens. We need interactions. And this brings us to the second part. What kind of interactions? In principle, you can solve the Schrödinger equation for any interaction that you want, right? It's a V of x there that you can put anything. Usually we put stuff that we know how to solve, right? Which I think it's three things. I think we know how to solve square well, harmonic oscillator, and a hydrogen atom. I think maybe we can also know how to solve delta potential. But in principle, you can put any kind of interaction there. However, and if you remember nothing else from this talk, remember this. There is a real way, there is a good way to actually choose your interactions. You may remember from electromagnetism that you can have something called minimal coupling. That's a prescription of how to write the interaction term in the electromagnetic Lagrangian. But that's true, but it runs a little bit deeper than that. So let's think about electromagnetism for a second. You know, better than me probably, that the electric and magnetic fields, they can be described in terms of these potentials, right? You know this story. Now, one thing that electromagnetism has that is very curious is that it is invariant under something called a gauge transformation. What does it mean? It means that if I make this transformation at the same time in the scalar potential and in the vector potential, the fields are unchanged. The fields are unchanged, everything else is unchanged. Notice that here it can be an arbitrary chi. Whatever I put here, it can have any dependence on x and t, on space and time. If you just do this, electromagnetism stays the same. Cool, so what? Of course, at this level, it's just a curiosity, right? It's useful because it helps us solve problems. If you're solving one of those hairy problems of electromagnetism in Jackson's book, probably you should be working on the right gauge, or else it will take you a lot of time. But there is something deeper. Consider now here, this is a classical Hamiltonian, okay? Forget for 1 second anything quantum. This is the Hamiltonian that, and here you see the minimal coupling, that gives rise to the Lorentz force. Fine. Suppose that I actually went and said, okay, let's go and make quantum relativistic mechanics, relativistic quantum mechanics. Then you know the drill, right? P goes into minus I del, the energy goes into I del T, And bing, you get this equation for a quantum particle in an electromagnetic field. What's interesting here now is that you can group this term, and you can write it like this. Which is suggestive already, right? Because you have something like a square part, but here you have only, this is quadratic, and this is linear. And this already lies at the heart of some problems. Because if you want to really do an electromagnetic, a relativistic equation, you should treat space and time in equal footing, right? How can an equation that has two derivatives in space and one derivative in time be relativistic? It's a tough call. But let's continue. On the other hand, if you take the free Schrödinger equation and you make this substitution like this, you arrive at the same equation. Fine. Now, the million-dollar question. And this is literal, right? Because people got the Nobel Prize for it. But if we make this gauge transformation, okay, take the phi, take the A, make the gauge transformation. So make this thing, make this transformation here. You will get another phi, another A. Therefore, you get another D. And another D0. And does the solution of this equation describe the same physics? And the answer is no, because you have extra terms floating around. It will not be the same physics. But Thiago, didn't you tell me that 5 minutes ago that if you make a gauge transformation, you don't change the physics at all? Isn't that the whole point? Yes, but then if you actually do it, you will see that this is not the case. What is missing? You're missing a phase transformation in the matter field. You also have to change the wave function by this factor here. And notice the gift here. Notice that we know that if you make phase transformations in wave functions, as long as they don't depend on space and time, we're golden, right? We know that. But here, this guy depends on space-time. Look, chi is here. So this is special. This is not a regular run-of-the-mill gauge transformation. So if you actually do that, then you will have the derivatives transforming like this. You will have this space-time dependent phase, and then you run the calculations, and then you get, in the end, this. D0 prime phi prime, psi prime, goes like exponential of IQ chi D0 psi. So this thing here transforms just like, this product here transforms just like the psi prime. And now the Schrödinger equation maintains its form, because if you do all of these, again now for the gradient term, we will get this. And now you will have exactly the same form as this equation here describing the same physics. And what do I mean by describing the same physics? For instance, everywhere, psi square is equal to psi prime square, and the Schrödinger equation maintains exactly its form. There are no spurious terms. And this seems to be a coincidence, right? Again, notice there is no reason for a phase depending on space-time to be a good transformation in quantum mechanics. Global phases that depend on nothing, it's okay. We know that from quantum mechanics. But this seems to be strange. However, it works. If you make the gauge transformation in the electromagnetic field and this phase transformation on the matter field, on the psi, at the same time, then it works. Strange. And the most interesting thing is that if all of this discussion can be subsumed if you make this substitution here, everywhere, you get this property for free, that you get the gauge transformation and the phase transformation together at the same time. And also, this current here also becomes gauge invariant, because it goes like this. This psi star prime transforms with this term. This d prime psi prime transforms with this term. These two guys cancel, and they still have the same thing. Seems miraculous. And now, can we reverse the argument? Can we demand that the theory is invariant under the space-time dependent phase transformation? So under this phase transformation of this form here, and then imposing the form of the interaction with the gauge field here? This is deep, right? This is saying, I don't need to put by hand the interaction. I just need to say that the theory is gauge invariant under local gauge transformations. Can symmetry really imply dynamics? Of course, the answer is yes, right? That's why we're here trying to teach you this. Now, assuming that this is the case, let's start with the thing we know the best, quantum electrodynamics. So again, start with this free electron Lagrangian, impose the invariance under this transformation, then make this, exactly this, del me goes into d me, which is del me plus I e a me, and a me transforms like this. And this alpha is the same guy as this alpha here. And when you go back and add this stuff here in this Lagrangian, you immediately get an interaction term in between the photon and the electron. And then you have photon, electron, the thing you're missing is the electromagnetic field. So you add the free photon Lagrangian, and bing, you have here the QED Lagrangian. And this works. Notice that you could have, in principle, in classical electrodynamics, a term like this, right? Because it is Lorentz invariant. But they are forbidden, because they break the gauge symmetry. This guy does not stay invariant when you do this transformation here. So if you're telling me my Lagrangian, my system has to be gauge invariant, you cannot have this thing here. And indeed, as you know, and as it has been measured again and again and again, the mass of the photon is very small, is compatible with 0. Now we have an interaction. It is like this. This is an interaction in between one photon and two electrons. And you represent it by this kind of diagram here, which is already our first Feynman diagram. And of course, this is just a gigantic simplification, right? This is like the 4th month of quantum field theory already. But the idea is that this A-me, it goes like A plus A dagger. This psi prime, so psi bar, has terms like this, and this psi has terms like this. And then you can use this formalism to calculate transitions in between, for instance, E plus E minus going to gamma, or E minus going to E minus gamma. Which, of course, this thing by itself doesn't happen because it doesn't conserve energy momentum. But you can make more calculations and stuff like this, just using these rules. And then you can have electron-positron annihilation or electron-electron interaction. And does this work, Thiago? Aren't you just feeding us a scoop of ice cream? Let's test it. Nature is the final arbiter. So if you go back to Dirac's equation, and now I'm putting it on this form here with the alpha and the beta which was Dirac's original form. And if you do relativistic quantum mechanics, you usually use this. You can make the approximations of low, almost not relativistic regime, get the large component of the spin, or you get the Pauli equation, okay? Look at these two. These two here is the interaction between the spin. This comes out natural, okay? This the Pauli equation comes out naturally with some approximations from the Dirac equation. And it gives you the interaction between the spin and the magnetic field. This is what we call the gyromagnetic factor. Dirac equation predicts 2, but you don't solve this equation analytically. It's hard. You solve it perturbatively. And if you do perturbatively, you do perturbation theory, you do a series. And then if you add more terms to the series, you get some deviations from 2. These deviations are parameterized by the anomalous magnetic dipole moment AE, which is this. At 3 level, AE is 0. But Dirac's theory, if you do in quantum mechanics, you can have higher order approximations, which in the jargon we call loops. Because why loops? Because it's stuff like this. And this will give you a non-zero AE. And this thing gets contribution not only from quantum electrodynamics, but from the rest of the standard model as well. What is usually done is that you parameterize it in this form here. And these coefficients, this alpha is really the, como é que chama isso em inglês? Fine constant, fine structure constant, 1/137 more or less. And these coefficients are dimensionless and they are universal. They don't depend on the lepton flavor. So they are the same for electrons, muons, and taus. If you do the calculations, and there is a guy in Japan called Kinoshita who makes his living by making these calculations. Good physics, actually, okay? I'm not shitting on the guy. But there are thousands of diagrams to make these calculations here. And you see here when the year where each of these terms was calculated. So here are the 72 diagrams that contribute to the third order term. And all of these, for each loop, so for each closed loop here, for instance, here you can count 1, 2. Each of these is one integral. So it's a big amount of work. But it has been done. And to measure it, you trap the electron in something called a pinning trap, and then you measure the spin flip frequency for a given magnetic field. And then you can calculate the gyromagnetic factor and the anomalous moment. And you see here the history of the measurements with the uncertainty. And it stops at 1987 because then we have this. So this is the experimental measurement, and this is the theoretical one. And there are 9 significant digits of agreement. This is, as far as I know, the best measured quantity in physics. So it works. This is just one example, but then again, you can go and search the literature, and if you come to the conclusion that quantum electrodynamics works beautifully. So let's start running the crank. I have quickly spoken, but I haven't explained. Standard model. So what is in the standard model? In the standard model, you have 2 kinds of matter particles, quarks and leptons. And what's the difference in between them? Quarks feel all interactions, strong interaction, weak interaction, and electromagnetic interaction, while leptons don't feel the strong interaction. But yeah, what is a strong interaction and the weak interaction? Easy. They are the interactions that we're going to propose in the following slides. I can give you, verbally speaking a bit, some ideas on that. The strong interaction is what binds the hadrons together. Protons and neutrons inside of the atom, they are made of quarks, which are these particles here. And they are bound systems by this interaction. The equivalent of the van der Waals interaction of this thing, van der Waals is for the electromagnetic, right? But it's the remnant electromagnetic interaction of a system which is neutral but made of charged particles. If you do the translation of all of these to the strong interaction, you get something which is sort of like the strong interaction remnant, and that is the interaction that manages to bind protons and neutrons together in the atomic nucleus. Because it's strange, right? You have protons which are positive, neutrons do nothing. How come those things make a bound state? So that's what the strong interaction mainly does. Weak interaction is mainly related to beta decay, experimentally, and a series of processes. But it's yet another interaction. And one of the highlights is that it's one of the interactions important for the nuclear reactions inside of the sun. Now, just like we imposed a gauge symmetry and got QED, we're going to do the same for these new interactions. And we're going to do the following. We're going to impose an SU3 gauge symmetry for the strong interaction, which is quantum chromodynamics. I'm already giving you the name. And an SU2 times E1 for the electroweak interaction. What is electroweak? Electroweak interaction, the idea is the following. There are actually only one interaction, the electric and the electromagnetism and the weak interaction. But this is at high energies. At low energies, the system, the fields undergo a phase transition, and we see it as two separate interactions. This is not just a simple technicality. This is important, but I won't really have time to speak much about this. But the point is that you have three interactions and three gauge groups. It's not that this U1 here is the electromagnetic phase. It's not, but it's related to it. And then quarks and leptons, I already spoke about it. And just like the photon appears in the when you do the gauge invariance on the Dirac-Lagrangian, other particles, the so-called gauge mediators, appear when you impose gauge invariance on the system. The photon for the electromagnetism, of course, the W and Z bosons for the weak interactions, and something called the gluon for the strong interaction. And this is all well and good, but there is one more piece that I'll quickly talk about again, because my time is almost over, which is the Higgs boson. So you add a scalar field, and one of the consequences of this scalar field is the appearance of a spin-zero massive particle called the Higgs boson. QCD in one slide. Oh, forgive me, Father. QCD in one slide. Now you just run the whole procedure again. There are subtleties, but the idea is that you choose the symmetry group, and then since it's SU3, this means that the matter fields, they transform under the fundamental representation of SU3, a triplet. So you need three charges. We call them colors, and obviously we call them red, green, and blue. The mediator, the quantum of the gauge field is the gluon, and it comes in 8 bicolored varieties, stuff like blue plus anti-red, things like that. Why 8? Because they transform under the adjoint representation. So there are 8 generators in SU3, because it's 3 times 3 minus 1. Is that right? The gluon, notice that the gluons, they are bicolor. They carry color themselves. They are charged. It's not like the photon. The photon is neutral. But the gluons themselves, they have charge. And this is important. This will lead to one of the important things. So besides the interaction, remember in quantum electrodynamics we had E gamma, electron, that half of that thing over there. Here we also have quark-quark gluon, but there is also gluon, gluon, gluon. So there is this, there is this, and there is this. But notice that there is no such thing as this. The photon doesn't interact with itself because it's neutral. And one thing that's important is that it's renormalizable. What is renormalizability in 20 seconds? When you do these calculations, and you do higher order calculations in quantum field theory, sometimes you encounter divergences in many aspects, infinities. And well, except maybe for black holes. There are no infinities in nature, right? There are no singularities. So how do you solve this? You have a collection of techniques, renormalization, to address that. And the whole point is that you can have infinities in your theory, but the things that you observe, the things that you measure, they have to stay finite. And then there is a whole field of physics, and there is something called a renormalization group that explains that helps you understand how those renormalization techniques work. There is a whole field of quantum field theory. But the bottom line is that a non-renormalizable theory is not amenable to standard perturbative calculations. If you try to run your quantum, your perturbation theory on a non-renormalizable theory, you get garbage. So there is renormalization to help us with that, but there is a price to pay. The constants become dependent on the interaction energy scale. And in particular, in the case of QCD, because the glue interacts with itself, there are some additions to how this coupling scale changes. And this is just the expression that comes out from the first loop calculation, the first order of perturbative theory, that shows you that the coupling strength changes like this. And what does this mean? High coupling strength means very tight coupling. Low coupling strength, high energy, means the quarks are almost free. And this is something that we actually observe. This fact that for high energy of high interaction energy, if you try to look at a proton with a very high energy probe, you can make out the quarks to be almost free. This is called asymptotic freedom. And this has been proved rigorously. On the other hand, for low energies, that means when you try to see the proton from afar, alpha S becomes very large. So this means that you cannot ever separate two quarks, because this coupling strength becomes so large that eventually it is energetically better for the vacuum to give up another quark-anti-quark pair and make new bound systems. This has not been proved rigorously, okay? But it's a fact that we have never observed isolated quarks. They always come in hadrons, which are bound systems of 2 or 3 quarks, called mesons or baryons. There is some new stuff happening. There are multi-quark states, but I'm not going to discuss them here. And of course, again, see here that this is well measured, and it seems to be the case. Now, when you do this kind of calculations in Feynman diagrams, one of the things that you learn is that the particles in the beginning, in the initial and final states, they have to be free in order for it to work. And then you tell me, well, Thiago, but then the theory is still bored, because you cannot have 3 quarks and gluons to start your calculations. But remember, inside of the proton, they are quasi-free. The idea is that you can use something called parton distribution functions that tell you what's the probability of finding a given quark or a given gluon carrying a given fraction of the momentum and energy of the proton as a function of this fraction. So you use these parton distribution functions, which you can study by probing the photon with high energy photons, for instance, to help you make these calculations. But then you do not do anymore, let's say, gluon quark going to something else. You have to do proton-proton going to something else, and take into account these PDFs here. The same thing in the final state, by the way. You cannot have this free quark here. What actually happens is that, how we model it, is that when you do more orders of perturbation theory, it's like these guys radiate. They start losing energy here in the form of gluon radiation, and the gluon can open up in quark and anti-quark pair again. And every time that they radiate, they lose energy. But every time that they lose energy, the coupling constant goes up. So it goes on and on and on until effectively it goes out of the perturbative theory regime. And there is a phase transition, and this becomes hadrons. And this is the process which we call parton showering hadronization. One thing that you also learn in QFT is that when this kind of stuff happens, usually these emissions here, they are either collinear or very close to collinear or very low energy. So what does this mean? If you have an isolated quark going and it starts radiating, eventually the whole system goes in the same direction. And then the hadrons will all be in one direction, more or less. It's a spray of hadrons, which we call a hadronic jet. So we cannot detect the quarks and gluons, but we can detect hadronic jets that, if everything goes all right, they should be, their kinematics should be representative of the original quark and gluon. Electroweak model in one slide. Same old song. Symmetry group. You have 6 flavors of quarks. You have 6 flavors of leptons. Why 6? And they come in families, right? I'm quickly going to come back. They come in families. First family, second family, and third family. Protons, neutrons, protons and neutrons are made only of the up and down quarks. Electrons are electrons. All of nature, standard matter, is made up only of the first family. Why are there 3? If you ask one of my theorist friends, they'll tell you that, oh, but you have to have 3 because of the anomalies, which is some technical reason, which is true. But then again, okay, why 3? It's still an open question. The point, again, this is super fast, but the point is that you group these particles, left-handed particles. This is a technicality relating on how they transform. And they form what's called isospin doublet. What's an isospin doublet? Their charge is SU2, right? So their charge is sort of kind of like the spin. It has the same mathematics as a spin. And then you have left particles that are doublet and right-handed particles which are singlet. So they are neutral under these transformations. And this is for the SU2L. That's why the L is here, because only the left-handed particles have this charge. But everybody also has a hypercharge. And a particular combination of these two is what gives you the electric charge in the end. And then again, you have the quantum of the SU2 gauge field is the weak bosons, W1, W2, W3. And for the other field, you have something called the B boson, the theories were normalizable, and we are happy. Except, as if you may notice, this has nothing to do with what I said before. In particular, it has nothing to do with nature. So this is completely wrong. What is missing here? One other thing. If you study Dirac Lagrangian, you will see that fermion mass terms, they have this structure which you can open up like this, and this thing has mixed symmetry. You cannot mix left, right, and left with right like this, because then it will not be symmetric. So this is a bad theory, right? Because your fermions don't have mass, your electron doesn't have mass. And remember that I told you that there could be no mass terms for the photon in QED? This is also true here. But the W and the Z bosons, they have mass. So this theory is completely worthless, except that it can be saved. And it was saved. How? You add to the Lagrangian an extra field, a complex scalar field phi, with these terms here, and this guy is again a spin doublet. You choose the hypercharge suitably. And the whole point of this thing is that you choose it such that its vacuum expectation value is not 0. What does it mean by that? If you make the expected value, Bryan cat, of this field with 0 and 0 on both sides, so literally this kind of thing, this is not 0. For this particular field. This is strange, but okay. The point is that this leads you to a situation where the ground state doesn't have the same symmetry as the whole system. There are many ways to talk about this. Ferromagnets, if you have studied solid state physics, condensed matter physics, they have these, right? Nature is symmetric in all three directions, but if you pick up your random ferromagnet, you will see that the spins are aligned in one direction. Why? Here's the same thing. If you have this kind, you can think of this really as a physical potential, like a ball in a mountain. If you have this kind of potential, this point here is an equilibrium, but it's an unstable equilibrium. You'll never find the system here. You'll find it here. But why here, or here, or here, all around here? All of these states are equally good, but it is in one of them. And all of these are connected by the symmetry of the system. And the things that, since we are here, we say that the SU2 symmetry is broken, just like we saw in the morning. This is the spontaneous symmetry breaking for this particular case. Spontaneous symmetry breaking happens in a lot of fields. And if I remember my history correctly, high energy particle physicists stole it from the solid state people. And the point is that then you rewrite this field here in this form here. This guy H now has the vacuum expectation value of 0, and this is the vacuum expectation value of the phi field. And then you rewrite the Lagrangian in terms of this thing, make a field rotation, gauge away, make a gauge transformation to get rid of these other fields, the Goldstone bosons, and everything will work out. You will have mass for the W, mass for the Z, but not mass for the photon. And then if you make couplings like this, you can get mass to the fermions as well. But one last field remains, which is the H. This guy remains, and its quantum is the Higgs boson. And its mass was a free parameter. All of the other parameters of the standard model, you could get it from low energy physics. From alpha, from Fermi's constant, from the Weinberg angle, which is the ratio of the W and Z masses, but not its mass. And the Higgs properties are exquisitely dependent on its mass. Here you see the cross-section, here you see the branching ratios. The whole point of the LHC was to find this thing. Great success, we did it. And all of its properties are actually expected by the standard model with this particular value of the mass, which we have no idea where it comes from. So here is the peak when you catch the Higgs boson decay into 4 leptons through 2 Z's, and here are the couplings. So all of this picture, what can you get from this? How do you actually do calculations with the standard model? It's a complicated thing here, but You calculate your hard matrix elements from the perturbative QFT. You embed some partons in protons through the structure function. So here you have the proton, and you have to get the partons from there. Add corrections for higher order perturbative processes, like initial state radiation, final state radiation, what happens to the rest of the hadron after it breaks down, hadronization, then some particles may be unstable, they decay. And then you just make a lot of calculations and get answers for the processes you're searching for. Of course, this is 2019, so we don't do these things by hand anymore. So tools of the trade for you, there are some packages. Fine rules is something that it gives you the Feynman rules if you feed it a Lagrangian. Then you have some software for matrix element calculations, CalHep from Sasha Pukov and Sasha Belyaev, MadGraph from, I forgot his name. I'll tell you later. Then you have Herrig and Pitya for the parton showering hadronization step. They also do the perturbative part, but they are not specially tuned for that. And then if you want to share with your coworkers, you have to have some standard data formats. So UFO for the universal fine rules output, LHE for when you want to calculate share events that come from a quantum, perturbative quantum field theory generator, and HepMC if you want to share the whole thing. So in 1 hour and 5 minutes, this was the theory. But this is only half of the story. What has to be done now is to actually detect those particles, interpret the events that we're seeing, and making some statements about nature. This is what I do, okay? Again, I'm an experimental physicist. If you ask any of the theorists, some of them have already left the room in disgust. It goes much deeper than this, okay? But this is the level at which us experimental high-energy physicists work. Thank you very much, and questions? Should I give you the microphone or something like that? Hello? No. Yeah, but then it won't be recorded. Okay, fine. I'll repeat the question. Go ahead.
Well, you mentioned some corrections for the data that you get. I was thinking, how robust are these corrections for the data? I mean,
corrections for the data?
Correct. Well, you said
for the simulation, for the calculation.
You mentioned.
Where? 3 slides ago. Here. Here. No, so I don't correct the data. The data is king. I correct the calculations. I correct the simulation. Data is what I observe.
I understood wrongly, I guess.
Okay, but how trustworthy is this? It's iterative. You can have it's semi-perturbative. You take perturbativity until you can take it. Then you have to model. How you model depends on how well you understand your theory. There are some non-perturbative things that can be done. Eventually, you tune it. So you go back to the data, compare with the simulation, and if your simulation is okay, there are some parameters that you can tune. And then you try to tune to reproduce the data, and then you iterate. Onde? Tell me.
I do not understand how the Parton method can explain the proton behavior with the quarks and gluons.
You cannot understand how the quark behavior, how the QCD can explain that the proton exists?
No, not the Parton model.
Okay, the Parton model. Parton model is something else. It's QCD with partons. Huh?
Yes.
What's the question?
So I do not understand, like, what's the purpose, simply stated, of the Parton? The partons.
The purpose is the other way around. Why do we do this? Why do we do QCD? Because it works. right? It's a copy of QED. Quantum electrodynamic works. Then somebody comes with an idea. Hey, let's do with a different gauge. Probably the history is a bit different than that, okay? There is a lot of different history. But bottom line, you take QED, you change the gauge group, and you get QCD, and then you run the calculations. And then you go back to the data, and it works. It describes the data very well. And we know how to do it because, as I said, it's a renormalizable theory. You can do perturbation theory. It's something very close to what we already know how to do. If it didn't work, then it would be a different thing. But it follows this gauge principle, like the others, so it's good.
But I think my question was, what is the patterns you described, and how can these can help the calculations match the experimental data? If you make calculations with partons, how can you match the experimental data? You have to do all of this calculation all the way to the proton collision. With the partons, you do nothing, you're right. But if you do all of this stuff here, then you can get the results of, oh, if I collide two protons at such energy in such a way, I should observe this, and that. And that you can compare with data. It's not only the partons, you need everything else. I'm either the best or the worst lecturer in the world because nobody's asking. This is the only thing. I just needed to speak about this, okay, to kickstart the lectures. I won't be speaking of theory any longer. Next lectures are interaction of radiation with matter, data analysis, data reconstruction, data analysis. Then maybe you understand even less, but. Okay, then. Well, there is a question there.
You talked about the calculations, the difference the calculations using QFT to obtain that you can obtain naturally the particle, the antiparticle, particle and antiparticle.
Yes.
It comes naturally. You used the A and A dagger operators, creation and annihilation. What's the comparison similarity with the B and B dagger?
So the question is, if you take the A and A dagger, one creates particles and the other creates antiparticles. No, sorry, one creates and destroys particles and the other creates and destroys antiparticles. You can show using results from Lorentz symmetry and so on and so forth that if your field is complex, these guys are actually independent, have to be the independent degrees of freedom. And then if you run the calculations, you see that you can either interpret whatever they create and destroy either as a particle with negative energy going back in time or as an antiparticle. Then you take the antiparticle interpretation. I think it's that, right? A particle going back in time with negative energy. This all roots back to the problem of negative energy on the Klein-Gordon equation, on the Dirac equation. There you see states with negative energy, and if you believe that those are wave equations, you cannot really say what the hell is a particle with negative energy. If you take this broader view that it's a field and there are particles and antiparticles, then you can make this other interpretation. Of course, you need experimental confirmation. But then the positron was already around. So you had the evidence of antiparticles. I'll go to you because I cannot hear very well. Fala.
I'm not sure if you talked about it and I just don't get it, but how I know what is the symmetry group my theory needs to follow? Because it looks like I'm giving a guess and then I see if it works.
So, again, I am an experimentalist. My job is to take the theories and take them to the back and shoot them in the neck. From what I understand, you want you want continuous symmetry groups, or sometimes continuous symmetry groups, but quotient with stuff like this, quotient with discrete symmetry groups and stuff like that. From what I can see, it's a bit of creativity, but you're constraining your creativity. First, you could say that you could add any function to the vector, to the potential term in the Schrödinger equation. Now you are constrained. Now you still have, as a theorist, now you still have the creativity, but in these bounds, but you have to choose a symmetry group. There are a lot of symmetry groups. And you run theories for all of them and try to find evidence of them. And if you don't, give up on them. I'm not sure that it can be any symmetry group. I know that it has to be continuous or quotient with a discrete one like this. And then you can also play a game like, you can say that, for instance, like we did in the standard model, left-handed particles transform like doublets of SU2. Right-handed particles transform like singlets. You can also play these kinds of games.
Gyromagnetic factor of the electron. The experimental precision and the theoretical prediction still don't match to the last significant digit. Of course, that is expected. But is there some type of, is that evidence of new physics possibly?
What do you mean they don't? They do, right? Come on, if you take a Z compatibility test in between these two things, they are the same. Now, since you spoke about it, of course I lied to you. This is for the electron. If you do the same calculation for the muon, there is I don't know how many sigmas of difference. Nobody understands it. And people think it may be signs of physics beyond the standard model. I don't know the numbers by heart, but yes, for the muon there is a gigantic discrepancy. To solve it, either, because for the muon, right, you have these other terms that are, you have these other, these ones only depend on one lepton flavor. These ones mix more. So for the muon, both the theoretical calculation is more complicated because I have to take account of the others. And the muon is not stable, so it decays. So it's harder to measure its gyromagnetic moment, but we do it. And there is a discrepancy. To solve this, there is a big experiment in Fermi. I'm not going to call it gigantic. Call it G-2 of the muon, which aims to measure this with more precision and try to see if there is actually such a discrepancy. Thanks for the question.
If there are no more questions, let's thank Thiago. I think we are good for today, right? There's nothing more to discuss.
Yes. Well, there is dinner, right?
Usando o mecanismo de Higgs, dá para prever teoricamente qual é a massa do tubo que vai ter, né?
Isso.
Fica...
Dá para você botar uns certos... Quer dizer, hoje em dia já não tem, hoje em dia tem Higgs lá e pronto. Dá para você botar uns bounds, dizer, olha, se ele for muito pesado, o negócio fica ficando perturbativo. Aí você começa a ver uma coisa estranha. E muito leve já tinha sido procurado, não tinha sido achado. Então ele está ali entre 100 GeV e 1 TeV. E aí você procura nessa range. E aí a gente achou.